Today we're going to talk about addition. The first thing we want to do when we talk about addition is talk about like terms. Like terms are terms in which variables and their exponents are exactly the same. For instance, 3x squared and 2x squared are like terms. 4x squared y and 7x squared y are like terms. Even though these both have an x squared, this one has a y, so this and this are not like terms. Just like 3x cubed y squared, these have different exponents, so this one is not a like term with these two or with this one. Another form of like terms are terms in which the units are the same. For instance, 4 inches and 7 inches are like terms. What's not a like term is 3 inches squared. The exponent is different here, so they're not the same. And then rational expressions in which the denominators are exactly the same. So 1/5 and 3/5. 2 over x minus 5 and 4 over x minus 5. Those are like these two are like terms and these two are like terms, but they're not like terms together. Addition is the process of adding two or more values together that are like terms. When performing addition, you have to have like terms. It doesn't make sense to add things that are not like terms. For example, if we wanted to add 4 plus 3, here's 1, 2, 3, 4 stars and 1, 2, 3 stars. So we have 4 and 3 makes 1, 2, 3, 4, 5, 6, 7. So that makes 7 stars. Versus if we have 4 stars, so we have 4 stars and 1, 2, 3 triangles, it doesn't make sense to say we have 4 star triangles plus 3 star triangles. This doesn't make sense, so we cannot add these because these two are not like terms. Another way to visualize addition is on a number line or just using objects. So what we did before was we had 2 objects, so 2 rectangles, 4 of the same rectangles, and we did 1, 2, 3, 4, 5, 6. So we have 6 rectangles. Here we can start out with, we can use integers. Now remember I said like terms. Well, having just integers are also like terms. So we start out at 2 and we're going to add 4. So we had 1, 2, 3, 4, and we end up with 6. So 2 plus 4 is equal to 6. Here's another problem. What happens when we start having negative numbers? Negative integers and positive integers are still like terms, so we can add them together. But here we have negative 4 plus 5. So we're going to start at negative 4, and we're going to add 5 to that. So 1, 2, 3, 4, 5, and we end up with negative 4 plus 5 is equal to positive 1. Another way to look at that is we have negative 4 boxes. When our boxes are red, that means they're negative. When they're gray like they were before, that means they're positive. So we have negative 4 boxes, and we're adding 5 boxes. Now remember, in section 1.6 we had the property A plus a negative A equals 0, or negative A plus A equals 0. That was our additive inverse property. So here we have 4 negative boxes and we have 4 positive boxes. If we look at these, we can add those together and get 0, and we'll have 1 positive box left over. So that again equals 1 rectangle. Let's try another problem. Let's try negative 3 plus a negative 5. When we try negative 3 plus a negative 5, we're starting at negative 3, and we're adding negative integers. So when we add negative integers, we want to go to the left. So negative 3 plus a negative 1 plus a negative 2 plus a negative 3 plus a negative 4 plus a negative 5 gives us negative 8. The other way to visualize this is negative 3 plus a negative 5. These are all the same color, so we're not going to use that additive inverse property. Before, on the previous slide, it was 4 red and 4 gray, and that's why we were able to use the additive inverse property. These are all red, so we're just going to count like we did if they were all gray. 1, 2, 3, 4, 5, 6, 7, 8. They're all red, so it's negative 8 rectangles. Now remember, when we used our number lines before, we didn't have to use increments of 1 every single time. So this time, we're going to use increments of 10, because they're both, we have negative 10 plus 30. They're both multiples of 10, so we'll use negative 10 plus 30, negative 10 plus 10, 20, 30, leaves us at 20. So negative 10 plus 30 is equal to 20. This time we're going to have to use increments of 1/10, so that, because that's what's common with the two of them. So we're going to start out at negative 4.6, so negative 4, and now we're at negative 4.6, and we're going to add 7.3, so this is negative 4.6. And when we add 1 to that, we get negative 3.6. Add another one, we get negative 2.6. Add another one, we get negative 1.6. Add another one, we have negative 0.6. Now this is where it's going to get a little tricky, because we're jumping over the 0 line. We're going from negative integers, or negative numbers, not negative integers, negative numbers to positive numbers. So we have negative 0.6. That's 1, 2, 3, 4 tick marks in front of or to the right of negative 1. So when we add 1, we're going 1, 2, 3, 4 tick marks in to the right of 0. This is going to be positive now, 0.4. So when we cross 0, that's when we go from negative 0.6 to positive 0.4. And then we add 1 again. That becomes 1.4. Add 1 more, and we get 2.4. 1, 2, 3, 4, 5, 6, 7. So we've added 7, and now we want to add our 0.3. 0.1, 0.2, 0.3. And that gives us 2.7. This is going to be a little harder to do on a number line. So this one we're just going to add how we have learned for a long time. We're going to line the numbers up vertically, 4, 5, 2, 1, 52, and 543. Again, like terms, we have to line up the ones digits, the tens digits, the hundreds digits, and the thousands digits. That's why we started all the way back when we started. That's part of the reason why we started by defining all this. So when we add 4,521 plus 52 plus 543, we're going to add our ones digits first. So 1 plus 2 plus 3 is 6. 2 plus 5 plus 4 is 11. So we have a 110, and then we have to carry the 10 to make a new 100. And then we have 5 plus 5 plus 1 is 11 again. So we're going to have the 11 here and carry our 1, and we have a 5 here. So 4,221 plus 52 plus 543 is 5,116. If we have now we're going to add 18.2 plus 23.1, so 23.21. 18.2, and just like over here where we lined up the ones digits and the tens digits, the hundreds digits, there's only 1,000s digits, we have to line up over here too. So we have 23.21. So the easiest way to do this is to make sure your decimal points are lined up. Then all your other digits are going to be lined up also. And then we can add. So there's nothing here, so there's a 0 here. So we have 0 plus 1 is 1. 2 plus 2 is 4. Our decimal comes down. 8 plus 3 is 11. So then we carry our 1. And we have 1 plus 1 plus 2 is 4. So 18.2 plus 23.21 is 41.41. Now we're going to be adding negative 52.1 plus a negative 17.9. Now when we remember when we did this on the number line, when we did negative plus a negative, we started here at like negative 2, I think it was, and we went left -4, and we ended up with -6. So really, we kept our negative sign and we added the two integers together. We're going to do the same thing here. They're both negative, so we're going to have a negative in our final answer. And now we can just add the numbers without looking at the negative. So 1 plus 9 is 10, and we're going to carry our 1. Our decimal point comes down. Now we have 7 plus 2 plus 1 is a 10 again, and carry our 1, and then we have 1 plus 5 plus 1 is 7. So our answer to -52.1 plus -17.9 is -70.0. Visualizing fraction addition. So just like when we had our boxes for integer addition, we can do the same thing with fraction addition. So when we did, when we visualized fractions, we had 4 sevenths. That was a box divided into 7, and we shaded 4 of them. And we're adding to that a box that is still divided into 7, and we're shading 2 of them. Now these individual boxes, the large boxes are the same size, so those are like, and the divisions in between the two boxes are the same size, so those are like also. So now, just like we did when we had individual integers and we added 2 plus 3 and got 5, we had 2 boxes and 3 boxes and 5 total boxes. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 out of 7 boxes. So that becomes 6 sevenths. Our original box is 1 whole 1, and it's divided into 7, and 6 are shaded. And the 6 shaded come from the fact that we had 4 shaded here and 2 shaded here. What happens when we have to divide the boxes differently though? So we have 1/4 plus 3/5. So here's our first box, and we have 1 shaded out of 4 divisions. And we're adding our second. The larger 1 wholes are still the same size. And then we shade, we have this one divided into 5, and we're shading 3. So this one is 3/5 and that one is 1/4. Notice the divisions are, one is vertical and one is horizontal. That just makes it easier for when we want to combine them. So now we need to divide this box and this box separately so that they look, the divisions look the same. So if we divide this one into 5 horizontal bars, now it's starting to look very similar to this one. If we divide this one into 4 vertical bars, now all of these little boxes are the same. And we end up with, here we have 1, 2, 3, 4, 5 shaded, 1, 2, 3, 4, 5 shaded, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 shaded. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 shaded out of 20 boxes. This whole box is divided into 20. How does this look if we're trying to do it numerically without using our boxes? This is 1/4. That's what we started with, and we added 3/5. Now remember, we have to make equivalent fractions, so when we do this, we divided this one into 5. Remember, 1, 2, 3, 4, 5. We had 5 divisions. So the divisions got divided into 5. And notice even the numerator, the 1, this was 1 whole before, that also got divided into 5. The second fraction, we had 3/5, and we divided it into 4. Remember, we had this 1, 2, 3, 4 divisions. So we have 4/4. And remember, when we're finding equivalent fractions, we have to multiply numerator and denominator. So that equals this. Then this new visualization is 5/20. And this one is 12/20. And now when we have a common denominator, we can just add the numerators, and we have 17/20. Let's try 2/3. So this is 2/3. One box is divided into 3, and we shaded 2, and we're adding 5/6. 1, 2, 3, 4, 5, 6. We added 5/6. Notice, to get these to be the same as this one, we already have the 3 vertical here, so we just have to multiply this one, or divide this one into 2. So to get our common denominator, we just have to multiply by 2/2. And we're adding, so this becomes 4/6 plus 5/6. That's 9/6, which is 1 whole and 3/6. So you can write it as 1 whole and 3/6. Notice we could simplify this fraction. This rectangle has half of it shaded, so 3/6 is also 1 and 1/2. 9/6, if you remember when we were doing equivalent fractions, this would divide by 3, and this one would also divide by 3, and we're left with 3/2. What happens now when we have 3/x plus 2/3? 3/x, we have 3 divisions shaded, and here there's x divisions total. We don't know what x stands for, we just know that x is a number. It could be any number. It could be 5, and then we would have 5 here. But right now we don't know what number that is, so we're just going to say x. So this is x divisions. That's what that dot means. It means we don't really know how many it is, so those 3 dots means that it's x divisions. So this is 3/x, and we're adding to that 2/3. So just like before, we have to divide this first one into the thirds. So we're going to multiply this one by 3/3. And now this one we want to divide into the x divisions. So we're going to multiply this one by x/x. We're still adding them. So that becomes 9/3x plus 2x over 3x, which is 9 plus 2x over 3x. The 9 comes from these 9 here, and our 2x comes from the 2x right there. It's a little bit harder to visualize when you do this, but just try and see the similarities between dividing into x and, say, dividing into 5. But make sure when you're doing your common denominators you multiply by 3 over 3 and x over x. So let's add these without doing the boxes now. These already have a common denominator, so we just have to add the numerators, and we have 7/5. These two do not have a common denominator, but it's like when we had the 3 and the 6. 5 is a factor of 10, so we can do 1/5 times 2 over 2 plus 3/10. We're going to talk a little bit more about least common denominators in a couple sections, but for now, try and find the smallest multiple of the two. So 1/5 plus 3/10, we need to multiply the 5th by 2 over 2. So now we have 2/10 plus 3/10, so that's 5/10. And again, if we see, we can divide both the numerator and denominator by 5, and we have 1/2. The 7 and the 3 don't have a common factor, so for this one we're going to do like we did when they didn't have a common factor, and divide this one into 3 and this one into 7. So we have 2/7 times 3 over 3 plus 2/3 times 7 over 7. So that gives us 6 over 21 plus 14 over 21. So that is 20 over 21. This last one, we want to divide this one into 5 and this one into y. So we have 2 over y times 5 over 5 plus 3/5 times y over y. So that is 10 over 5y plus 3y over 5y. Now that we have a common denominator, we can add the numerators and have 10 plus 3y over 5y. The 10 and the 3y are not like terms, so you have to leave it like that. You cannot combine those two. Now we're going to start adding polynomials. Remember, we can only add like terms. So our like terms here are b cubed and b cubed. Another set of like terms is b squared and b squared. Another set is b and b. I find it easiest if we set these up vertically, just like we would with our decimal numbers. We're going to set up the like terms underneath each other. So this is, we'll start out with 4b cubed plus 7b squared plus 3b, and then come over here and we have 5b cubed, so we're going to put that vertically under that one. Under the 4b cubed, we have 4b squared, so we're going to put it under the 7b squared. And we have 2 plus 2b, so we're going to put that under the 3b. and then we have plus 5. I'm going to run out of room, so I'm going to come over here, but we have 4b cubed plus 5b cubed is 9b cubed. We have 7b squared plus 4b squared is plus 11b squared plus 3b plus 2b is 5b, and then plus the last 5 because there's a 0 here. Notice we didn't get 9b to the 6th. Remember, when to add exponents, we're actually multiplying, not adding. So when you start a problem, remind yourself what the operation is that you're doing, and then the rules that go with that operation. So for addition, all we're doing is counting up how many we have. Now this one, we have 4x cubed y plus 5x squared y squared plus 7, and we're adding to that 7x squared y squared. That's going to go under our 5x squared y squared plus 4xy squared. That's not like to this one, so we're going to, or this one, so we're going to put it off here, plus 4xy squared. Remember, addition is commutative, so we can add in any order. And then plus 10. This is plus 7, so we're going to put the plus 10 under the plus 7. Now when we add it all together, we have 4x cubed y plus 5x squared y squared plus 7x squared y squared is 12x squared y squared plus 7 plus 10 is 17 plus 4x y squared. A couple more. We want to find our like terms. So same exponent, same variables. Same exponents. Remember, the square root of a number is equal to that number to the 1/2 power. The cube root of a number is equal to that number to the 1/3 power. So for same exponents, we're also looking at the same radical and what's underneath that radical. The radicand has to be the same also. So here we have a square root of 5, and here we have a square root of 5. So we have 2 square root of 5 plus a negative, remember minus is plus a negative, 3 square root of 5, so that's negative square root of 5. And now we have 4 cube root of 7 and 7 cube root of 7. So we're going to add 11 cube root of 7. And then this last one doesn't have a like term, so we're just going to add 6 square root of 2. Another one to look at, remember these are just complex numbers, and we're going to add the real parts together. So the 2 and the 3 are the real parts, so we're going to add 2 plus 3 is 5, and then we're going to add the imaginary parts together. 3i plus 7i is 10i. Now this last one, we're going to use like terms to add. We're not going to distribute first. So for like terms, if we have 3x plus 7x, we're actually adding the 3 plus 7 first and then the x. So 3x plus 7x is 10x. Here we have 3x plus 4, we have this x plus 4, and we have 7x plus 4. So we have 3 of this x plus 4 thing, 3 of this thing, and 7 more of this thing. So we have 10x plus 4. Doing this, and especially down here, is a precursor, something earlier than what we're going to do for factoring. So that's why we're doing this. Here we have y minus 4 and y minus 4. Notice the first step was to put the 3 plus 7 in parentheses. So we have y minus 4 and y minus 4. We're going to take 2y plus 3. We're adding those two together. And then we have y minus 4. That's our like term. So we have 2y of this thing and 3 more of this thing. So we're doing 2y plus 3 times y minus 4. This next one, we have 4 square root of 3x plus y times y plus 3 plus 2 square root of 3x times y plus 3. This looks really complicated, but notice this and this are the same. They're both square root of 3x times y plus 3. They're exactly the same, so that means they're like terms. So we have 4 of this ugly chunk and 2 more of this ugly chunk. So we end up with 6 total of that ugly chunk, which is 3x square root of 3x times y plus 3. That's it for today. Talk to you tomorrow.